I hope everyone is in good health in this brand new day. I am Ruth Kalista of Universitas Sumatera Utara, Indonesia.
And good morning to everyone. My name is Mark Christian Leda of Don Mariano Marcos Memorial State University, Philippines. Greeting you all. Magandang umaga sa ating lahat. That's how we greet in Filipino, saying good morning to all of us.
So, Mark, yesterday was a very jam-packed presentation. We had the two parallel session on data science and artificial intelligence, and also on informatics and digital technology.
Yes, it was indeed a great opportunity for us to listen to the different presentation from different schools and universities. We are also grateful that Dr. Leo Ray Marquez, the senior research scientist with the Digital Productivity Flagship at CSIRO Australia, shared his expertise as a keynote speaker and provided us with knowledge on creating effective evacuation plans with simulation-based tools.
I agree, Mark. So the Databia 2023 conference, jointly organized by Universitas Sumatera Utara and Don Mariano Marcos Memorial State University, presents a commendable opportunity. This conference focuses on adequately equipping businesses with the latest developments in artificial intelligence and analytics techniques to enhance their growth and success rate in digital era.
And I believe that this conference encompasses an innovative platform for the application of advanced technologies. This will definitely benefit different businesses in their quest for adaptability and sustainability at the forefront of a modern market.
So I'm sure that everyone is now ready for our second day. So without further ado, we will now continue our conference.
Indeed. Our keynote speaker is one of the main proponents of Japan, the Savannah solution in Switzerland, the Probe software in USA, and the Arimas in Brazil. He was an associate professor in Ateneo de Manila University in the Philippines, a visiting professor in Ateneo de Davao, Philippines, a visiting research fellow in the University of Wisconsin and Blackstone Incorporated, both in the USA, and the Hertha Firnberg Research Fellow in the Australian Institute of Technology, Austria. He was also a lecturer in Saga University, Japan, and in Petra Christian University, Indonesia. A round of a virtual applause to our keynote speaker, Dr. Cardi Teknomo.
Thank you. Yeah. Thank you for the opportunity to share this knowledge with you. Can you hear my voice well and the presentation as well?
Yes, Sir Cardi.
Yes. Okay. So for today's presentation, I would like to give an idea, okay, about how we can transform our creativity into combinatorial optimization problems. Okay. So particularly, I'm very keen about how we can create a systematic approach, yeah, to generate optimal alternative solution for the traffic congestion. Okay. So for today's presentation, I would like to divide into 5 parts. Okay. The first part is the background about what is ideal flow network. Okay. And then I will go to the background on the problems and then the resolution of this, how we can transform creativity into optimization problem. And then we will end with the demonstration. Okay. Okay. First part is about ideal flow network. Okay. So what is ideal flow network or IFN? Basically, IFN is a steady state relative flow distribution, okay, in a strongly connected network where the flow are conserved. So you probably think, what is this? Is this a neural network? No, this is just a simple strongly connected network, okay, where the weight of each node, okay, the sum of weight or in each node, the sum of input weight is the same as output weight. So that is the term premagic. The term premagic means the sum of flow, the weight is we call flow. Okay, the sum of all the flow in is the same as the sum of all the flow out. Irreducible here means the network is actually strongly connected. And this is based on Markov equilibrium. Okay. So everything will be represented as network with this directed graph or matrix. Okay. So we developed ideal flow network theory very long time, okay, since 2014. So basically, IFN is a strongly connected network where the flow are preserved, right? And then the matrix must be irreducible with the strongly connected and premagic. So this is the same thing. So which means the sum of input is the same as the sum of output in each node. Okay. Now we can form this network based on trajectory. So we can create this trajectory cycle, okay, and then it will always create ideal flow network. Okay, so the software is freely available in GitHub. So this is the links. Okay, if you don't like to use Python, you can also use Excel. So there is add-ins Excel available. Or if you don't like to do anything, so you can just visit the website. Okay, there are also online version of it, which you can also use in mobile phone. Okay, in fact, this is some of this will be used today in today's demonstration. So why are you going to use IFN, right? So what is the connection between traffic flow and artificial intelligence? Yeah. So basically, IFN is just a modeling tool. Okay. So when we said a traffic flow network, this is just a metaphor. Okay, and naming convention. Why? Because it was developed earlier based on a traffic network. Okay, so using this metaphor or jargon, that is easier to make because now you have several jargon. Like for example, it is irreducible. That means strongly connected network. Nah? The flow, that means the weight. Yeah? Congestion, that means the capacity divided the flow divided by the capacity. Yeah? Or the flow divided by the maximum flow. Okay. Premagic, that means the sum of input flow is the same as sum of output flow. So these are the jargon or the terminology that we will use in IFN. Yeah. So as long as any problem you can solve using IFN, as long as you can formulate it as flow equilibrium in the strongly connected network graph, then you can use this as your modeling tool. Okay, so again, the jargon seems like traffic, but you can apply it in any other field, including artificial intelligence and data science. In fact, a few of them I will introduce now. Okay, so these are some application of ideal flow network. So for example, you can use IFN for supervised learning. Okay, so the input X, yeah, is attribute, okay, or discrete data, either numerical or categorical, and the output is the classes, right? So we call this IFNC, or IFN classification. So in IFN classification, based on that IFN classification, so we can classify data table, okay, we can classify the text, and also do some image processing. Based on all of this is based on the same algorithm called IFN. Okay, IFN can also generate. Okay, so similar to neural network, it can also generate. For example, IFN can be used for music generation. Okay, so You can visit this website. Okay, so the peoplereferral.com and a tutorial. Okay, let's demonstrate this if you want. So I will stop sharing this and share the website. Okay, so this is the QR code. Can you see it? So you can scan this QR code to visit the website. Okay, and these are the menu. Okay, many IFN or ideal flow network laboratory, yeah, that we can use here. This one is the demo for music, and this is for the classification, yeah, supervised learning. So I will demonstrate this first so that you can see. So this is the, for example, we have several examples here. So this is transportation mode. Okay, so you have a cold weather, by computer and so on. So let's say this is the example that we want. So in the first row represent the variables. Okay, and these are the data. Okay, and say when you train this, there, okay, you can see the network. Né? So the three networks, and then this is the accuracy. Okay, so if you think that this is not enough accuracy, you can improve by increasing the parameter here with this Markov order. Okay, and this is the meaning of this hash code. Yeah, and based on that trained data, now you can generate the input. So this is an inverse function. Okay, and then you can of course do some prediction. So say for example, if you have this data, that means the bus with certain confidence level. Yeah. Similarly, come back here. You can also do the music generation, for example. So you can select several music here that you want. So I have a Mozart song. Okay. So now this Mozart song have this code, right? So now we can train that using IFN. Can you see? Now, once you train that, and then it will automatically generate a new song based on that Mozart code. But to make it in contrast, you can check in different song. For example, this is Burung Kakak Tua in Indonesian. And this is an Indonesian song. Now we generate based on that trained music Indonesian song. Okay, so you can click anytime. Now you can see that whenever the data you put in, okay, it will generate based on that data. Okay. So I hope this is motivating enough. Now come back to the slide. Okay. Right. So you can generate the music. Okay. Based on whatever music that you put in. Of course, you can create your own music here. Yeah? If you know the code of the musical code, you can train yourself, your own music. Okay, and IFN also can be used to train the image. No? Say this is for character recognition using ideal flow. Okay, and then we can predict with some confidence. Okay. So if you put the drawing here, it will predict the true label with say 100%. Yeah. So if it is not predicting accuracy, of course you can train again with certain Markov order. Okay, and the good thing is similar to PCA, principal component analysis. It will also generate the background. What is the actual image behind this train data? Okay, and IFN can also be used for text processing. So this is the prayer in Indonesian. Okay, and you can also predict and also can generate. Yeah, can generate back uh, the prayer. Okay, and I put for example, this is the story. Yeah. Um, and then it will generate random story. Okay, so this is the application of IFN in artificial intelligence. So back to the core presentation. Today's we would like to transform creativity into combinatorial optimization problem. Okay, so our goal is actually to create a systematic approach how to generate optimal alternative for traffic congestion solution. Okay, so as the background, traditionally this used by transport engineer and urban planner, right? But what happened is they rely on their creativity, to develop the alternative scenario for traffic congestion, right? So because their creativity is based on their experience, their knowledge, and so on. So this usually lead to the solution, which is just road widening and build more road to alleviate traffic congestion. So as a computer scientist, probably you talk to ask, what is the better solution? Is there any way to make this into optimization problems? So study by this Han 2017 show that actually creativity can be seen as random selection among combinatorial space. Okay, so basically we can say that creativity is combinatorial optimization, but we need to create that combinatorial space. So the idea is come from many years ago. Okay, I was in Ateneo, de Manila, in the Philippines, and I was tasked to develop a traffic scheme inside the campus and in Katipunan area. Okay, and for that purpose, we developed about 16 combination scenario, something like this. And then we selected which one is the best among all these. The total scenario is like 100 plus, and then we selected 16 feasible scenario, and then we select one of or two of the best scenario eventually. Okay, so at that time we do it manually. Okay, so now I would like to ask, is there any way to create more systematic framework? Okay, so that we can do using computer rather than manual work, which take tremendous a lot of time. Okay. Now, we want to transform this kind of creativity in quote into combinatorial optimization. So in that case, we need to apply the framework to develop the alternative solution. Okay. So I would like to highlight the term create and apply here in the Bloom taxonomy. So create is the highest, apply is like the third level. So let's define first. Okay, let's define the change. Okay, as policy. Okay, so we have what is called base scenario. Base scenario mean current condition. Okay, so you have the traffic network. Okay, I call this C0. So this is the base scenario with this current condition, existing condition. Okay. And then we will generate what is called policy combination. Yeah. And then it will create alternative scenario. Okay. So C1 is the alternative scenario based on C0, which is the existing condition. For example, oh, you want to widen the road, that means this lane you add the weight, right? The number of lane you increase. Yeah. So a policy is defined as a combination of changes or modification that would apply to the existing condition in order to, this is the goal, to improve the performance of the current condition, right? So when we set policy, okay, or change, that can be at any level. Okay, so you can put it in strategic level, which is very long term or macro. Okay, national level, for example, or you can put it in tactical level, yeah, or in technical level, okay, or below in the micro level in the operational. Yeah? So this is called the planning level, is strategic, tactical, and technical, or in the implementation, yeah, day-to-day implementation, which is technical and operational. Okay. Now, the idea is like this. Yeah? We have the current existing situation, so we call this base scenario. So we form that capacity matrix C0. Okay. And then we apply the policy combination again to become the proposed alternative capacity matrix. Yeah. So I start to introduce the name capacity matrix. Yeah. So what is capacity matrix? Basically, let's go back to the website. Maybe I can share the whole thing. Okay. So let's go to the website a while ago, the IFN. Okay. We go to this, you can scan this QR code. Okay. And this is just a toy, okay, where you can convert the matrix into network. Okay. So say you can click control and you can play with this. And when you click in this screen, you can see we add node, then the matrix will change. So then you can draw, then it will create a matrix here, or you can click directly here. If you do a right click, it will reduce. It will. If you do a left click, it will increase the weight. Yeah. So this kind of matrix, okay, the weighted adjacency matrix, we call this as a capacity matrix. Okay, so capacity matrix is basically a weighted adjacency matrix. Okay. Now, if you go to this lab, next, okay, from this capacity matrix, we can create what is called stochastic matrix. Okay, so again, the computation is here, the formula, so you just ignore that. Okay, so if you click this random capacity matrix, you will create, so let me zoom. Oh, okay, so now you can see the network and the matrix. Can you see that? Okay, so every time you click this random capacity matrix, okay, it will generate random matrix. Yeah? And then when you click this arrow, it will convert the capacity matrix into stochastic matrix. Yeah, this is the pattern of the stochastic matrix. Okay, so you can also put it into fraction if you want. So basically, the stochastic matrix say that the total sum in each row must be 1. Yeah. So from this capacity matrix with this weighted adjacency matrix, you can form a stochastic matrix. I hope this is clear. Yeah. And then from that stochastic matrix, you can create ideal flow matrix. Yeah. This is the formula you can ignore. Okay. So say you have the stochastic matrix like this. Okay. Or you can generate randomly. Right? And then you can compute the ideal flow matrix. Yeah. So ideal flow matrix depends on one parameter called kappa. Yeah, this is the total flow inside the network. Yeah? So for example, if you put it into 1 and convert, you get the probability of its link. Yeah? If you put 100, again, this is probability in its link with 100%. So this is convertible. Okay? So we can go directly from the capacity matrix a while ago to ideal flow network. So if you know the capacity matrix, then you can convert directly to IFN. Okay. So now back to this presentation. Okay. Our goal, okay, we have the capacity matrix, which is the current number of lanes in the network. Okay. And we want to know what is the connectivity and the number of lanes in the alternative solution. Okay. So for doing that, okay, we develop this framework. Okay, so this is the framework. Number one is we need to identify elementary policies. Okay, after that we need to do what is called validity test. Okay, once we can validate these policies, then we can generate the valid policy combination. Yeah? And then we apply the second test, which is feasibility test. And then the last one, of course, to source the optimum policy. And I will demonstrate it later, this framework. Yeah? So think about it like a chemistry. Okay. Say elementary policy is like you have some atom, like oxygen, hydrogen. Okay. So when you create the policy combination, okay, when you combine the oxygen and hydrogen, say 2 hydrogen and 1 oxygen, you will create what is called policy combination, which is a molecule. Okay, so analogy. Okay, so again, yeah, we start with the simple elementary policy, okay, and then we combine all of this, yeah, to create a molecule, and then we test whether this molecule or policy combination is actually optimum or not. Okay, so this is the simple framework. I hope this is clear. Okay, so for our scope of study, okay, we limit the study only on the impact, okay, of the change of the network structure. Okay, the network structure means interconnectivity in the network. Okay, toward the network utilization and the congestion. How we will convert say the map from Google Map or from OpenStreetMap, okay, or network structure, right, into network utilization, the flow and the congestion. Yeah. So in this case, we do not include, for example, car sharing, the change in vehicle occupancy, or the introduction of other modes, yeah? Or the change of land use, etc. Okay. So this is just limit within change of network structure to network utilization. Okay. So when we set transport policies, okay, we can change a lot of things. Okay, for example, you can change the weight or you can change the structure itself. Yeah, so you can apply to the number of lanes or to the road width, okay, or to the link direction. Okay, so here if you add the lane, yeah, you can apply temporarily or permanent. Okay, so this is the example of scenario. For example, you do on-street parking removal temporarily. That means you add more lane, isn't it? Yeah, whether temporarily or permanent. See, say you add road widening, for example. Yeah? So this is also you add additional lane, right? You can also reduce the lane, right? The reduced lane means the weight. Okay, now reduce. For example, you introduce parking on-street parking allowance, or you want to do some event. Yeah? Oh, there is a demonstration here, or there is a religious event, or some VIP will pass certain event. Yeah? Or you can make it permanent, like, oh, I want to use this lane for bike lane or for public park. So in this case, a permanent reduced lane. Or you can also add the width, right? So the same thing, yeah, on street parking removal on certain hour temporarily, or due to road widening. So this is add width, add road width, right? You can also reduce the weight because of the road construction. So we can analyze all of this example of scenario. Okay. So you can also add the links or remove the link itself, right? Or you can change the direction. For example, or what happens if I do a one-way street, yeah? Or certain link you make it into one way instead of two ways. Yeah? Now you can also add the lanes in the reverse direction, for example, during peak hour and so on. So again, these are your creativity. Yeah? The scenario is the creativity. So we need to apply this scenario into elementary level, yeah? Which is in this description. Okay, so with that, okay, we come back to the mathematics. Yeah. So in graph theory, we have what is called graph. Graph is basically a set consists of two sets, yeah, which is the set of node and the set of links. So our concern is a special case of graph theory, which is called ideal flow network or IFN, okay, which is strongly connected network. What is the meaning of strongly connected network? Strongly connected network means from your home, you can go anywhere and then you can go home. Okay, so transportation network must be like that, right? Because if it is not strongly connected, you can go somewhere, say you go to the mall or you go to the school, you cannot go home, right? So it is not strongly connected. So strongly connected network means you can go somewhere, okay, and then you can go home. So and then each node, okay, the flow must be balanced. The meaning of balance means the total inflow is the same as the total outflow. So these are the five basic operations, right? So you can add node, you can delete node, you can add the links, and you can delete the links, and you can change the link weight. Oh, how about the change direction? Well, change direction is actually the same as you delete one link and then you add another link in the other direction, isn't it? So, oh yeah, yeah. So operation change link direction, yeah, you the same as delete existing link and then you add the links in the other direction. So again, the order is not important. So this is a combination, right? Based on this graph theory basic operation, right? Now we can identify the elementary policies. Yeah. So I will put this as elementary policies, meaning the change that we can apply. So we can add lane, say from 1 up to n lane. We can add the link, yeah, from 1 up to a complete network. Yeah. A complete network means from each node you connect to any other node. Okay. In reality, this is impossible, of course. Yeah. Because it node represent the intersection, right? Now, you can also reduce the lane, say -1 up to -n, yeah? But you don't remove the link, yeah? So you don't make it into 0. If you want to remove the link, that means the next elementary policy, okay? So in this case, we need to be very careful so that the network still irreducible, means still strongly connected. Yeah? And again, also, if you want to reverse the direction of the link, okay, you need to make sure that they are still irreducible network, meaning still strongly connected network. So these are the requirements. Okay. Again, these five are the atom. Okay. These five are the atoms. So let's say this is an example of molecule. Yeah? Say you want to split link. What is the split link mean? So you reduce lane in the existing link and then add one link in the same amount of lane as the reduction of the other direction. That means the total number of lanes is in the road still the same. Yeah, the right of way still not changed. Another example of molecule is to adjust the lane. Yeah? So you split the lane of the two-way links. Yeah? For example, if you have a link A, B, 3 lanes, and then link B, A, 5 lanes, the total is 8, right? So then you adjust so that, for example, now become 4, 4. Yeah? Instead of 3, 5, you want to adjust become 4, 4. So adjust lane is a molecule. Why? Because it's the same as reduce lane in one link, right? And then add lane in the other link, right? Now, we have identified the policy, right? And then the next step is to test the validity. So this is what I propose as the validity test. Yeah, basically listing the minimum, the lower bound and upper bound value. Yeah, so the minimum is strongly connected, okay, and should be non-negative. The maximum is premagic. Yeah. Premagic mean in the capacity matrix itself, okay, the total number of lanes, okay, is the same. So in this case, the factor sum of row is the same as the factor sum of columns. Yeah. The total number of lanes in and out are the same. Yeah. So these are the 4 tests of the validity, okay, and for each of these elementary operation. Yeah. So we need to be non-negative, so must be larger than 0, okay, and should not be 0. Right? And then the third step in the framework is to generate exhaustively or random policy combination. Yeah, this is to generate the molecule, right? Now, a while ago I showed you that from the capacity matrix, which is the network structure, say from Google Map or from OpenStreetMap, okay, 0 means the existing condition, right? You can create the stochastic matrix. Yeah. So 1 is the alternative, and 0 means the existing condition. So from the capacity matrix, you can create the stochastic matrix, right? From the stochastic matrix, you can create the ideal flow matrix. Yeah. So with certain parameter called kappa, which is the total flow. Okay. Now from this capacity, okay, and the flow matrix, we can create a congestion matrix. Yeah. See? So this is the output. This is the 2 input. Yeah. So this is functional analysis, very simple. Yeah. If you know the input, this is the output. Okay. Now, if you know the congestion, which is just flow divided by the capacity, okay, now we can find the maximum congestion. So I will name this G0 and G1. Yeah? G0 for the existing condition, G1 for the alternative scenario. Okay, so if you look at this, okay, the stochastic matrix depends on capacity matrix, right? Now, ideal flow depends on stochastic matrix, right? So in that case, we can put in that ideal flow depends on capacity. So we can remove the stochastic together. So in that case, we can say that actually congestion depends on only the total flow and the capacity matrix. Yeah, if we so using this functional analysis, we can simplify that congestion depends on not depends on ideal flow itself, not depend on stochastic matrix, but directly from the input, which is the network structure, say from Google Map, from OpenStreetMap, and then if you know the parameter total flow, we can get the congestion directly. Okay. Now the process, a while ago, so you know the capacity matrix. Okay, you can calculate the stochastic matrix and the flow matrix, and then you get the congestion, isn't it? So basically congestion is a function of capacity. So this is what we put here. Congestion is just a function of capacity and the invariant, which is the kappa here. So these are the two input now. Okay, so this is simplified process. So now once you get the congestion matrix, you can identify which link is actually the congestion, the most congested. Yeah. So this is the maximum congestion. Okay. With that, okay, so we can apply different models. So this is the model for well-known model called Green Seal or Bureau Public Road. Yeah. So then you can get the delay, you can get the travel time, you can get any other things, yeah, including you can get the environmental costs or the pollution or for example, energy level and so on. Okay. Once you know the congestion level, you can apply any other model. Okay. Now, let's stick back to just congestion level because this is the basic. Once you know the congestion, you can apply any other model. You can get anything, any other performance that you want. Okay, so the basic is just congestion. Again, this GI, okay, is the maximum of I. I is the scenario number. Okay, depends on the capacity and the parameter kappa. Yeah? Kappa is the total flow in the network. Okay, so we can say that the total flow parameter kappa is actually the aggregated network utilization. Yeah, it is part of the system, right? And CI is the network structure, which is part of the system. So now in the fourth step in the framework is feasibility test. Yeah, so we will say a scenario combination is feasible, right? If this scenario alternative is actually lower congestion than the existing one. Yeah. So G1 is the alternative that generated based on that molecule a while ago, and G0 is the existing one. Okay. So if lower, okay, mean less congested, right? So this is what we want. Okay. After that, then we can just search. Yeah. So can see here now become combinatorial optimization problem. So we want to find C1, okay, out of Z0, yeah, so that G1 is less than G0. So now we can see that the creativity can be put into combinatorial optimization problem. Yeah. Okay. So this is the framework that I would like to explain. Now let's do the demonstration. Okay, so you can go to okay, so you can go to this page, so you can scan this QR code. So I explain here there are 5 modification, the elementary one. Okay, we can add link, delete link, change link direction, add link, and reduce link. Okay, in this page, we will only do add and reduce lane. Okay, so let's go here. So you can generate simplified network. Okay, you can change the number of lanes, the number of nodes here. Okay, so I generate, for example, 4. Okay, and this is the pattern, right? So if you want to add and reduce lane, so you can tell which lane you want to add, yeah, or you want to reduce. So this is positive mean add, this negative mean reduce. Yeah. So how many lanes you want to add? For example, so I want to add link BA, right? So BA is now 8. So I want to reduce by 2. Okay. Again, this is random, yeah. So I want to reduce by 2, so I click reduce lane, right? So when, remember this is, let me check. Oh, there. So initially 4, I reduce by 2. Yeah, when I click this arrow, it will become from 4 now become 2. Yeah. Okay. So this is just the help. So you can, why I created this so that you will know which link you can reduce or add. Okay. This is the valid links that you can reduce and add. Okay. And then say you can set the base scenario, what is the congestion level, say 0.8, and then you can compare this. You click the yellow button here, there. Yeah. Oh, the base scenario is 0.8. Yeah. Now the alternative now becomes 0.9, which is worse, yeah, not better. Okay. So you reduce the lane from 4 lane now become 2 lane. Oh, actually, the alternative scenario is worse than the base scenario by 14%. So this is not what you want, right? So you can select other combination here. Nah? So you can select other. Say, for example, I add now instead of reducing, now I add 2 lane in AD. There, I add to A. AD is here, 10 lane. Okay, so I add now become 12 lanes. Is it better or not? Okay, we check this. Oh, still worse, nah? Still worse, 14%. Now, how about we can do it manually like this, okay? But we can also do, okay, so I will report here at the bottom. We can also do finding scenario, okay, up to 10 directly. Yeah? This is the search button there. Yeah. So you can add scenario or you can reduce scenario. Yeah. Reduce the number of lane. So then when you click here, oh, this is interesting. Yeah, in this, again, this scenario is random, random network. Can you see here that when we, let me, this is PC. Okay, so when we actually reduce the number of lane, okay, in BC, minus 2 lanes become 3, from 5 lane to become 3 lanes. Actually, the congestion improve. Yeah, okay, the congestion level improve. So this is the simple proof, okay, that the creativity of the transport engineer and the urban planner are wrong, right? Because they always think that we always need to add the number of lanes, okay? We need to increase the number of lanes in order to solve traffic congestion, okay? So, okay. But actually it is not. You see, if I change this, okay, I reduce this based on this PC, right? Let's see BC. Okay, so I delete. So BC I add how many? Minus 2, yeah. So B
I'm sorry, Prof. Cardi, you're still muted.
I think your microphone is on mute, Professor Cardi.
Oh no.
All right, we can hear you now.
Okay. Sorry. So okay. If you visit this page, okay, using this QR code, okay, you can check the scenario comparison of either add links, delete link, change link direction, or add the lanes or reduce lane. Okay, so this is the example where you can actually remove the links. So first you can try to create random network here. Okay, and based on this random network, so this is the number of lanes, right? And these are the visible links that you can generate, that you can remove. So because the network is something like this, so you cannot actually remove. So in here, you can remove only these 4 links. Yeah, so say if you want to remove CA, CA is this one, then you can remove this link, CA. Okay, from 6 now becomes 0, and then you can compare. Oh, this is a example that when you actually remove the links, okay, you can also improve the performance. Okay. So if you click this find scenario, it will find all the possible scenario, okay, for removing the links. So, and when you click this, you can actually check how many improvement we can get by removing the links. Yeah. So when you remove DA, okay, you can get like 43% improvement. So removing the link is not necessarily make the congestion worse. Okay, the same thing you can also check with other scenario comparison. Okay, that if you want to reduce the lane, yeah, it's not necessarily you can make the congestion worse. Okay, so See, I can show here random network, okay, and then we can find the scenario of reduced lane, okay, that we can actually improve the performance, okay, by reducing two lanes, okay, in this link AC. Yeah. So now let me back to the slide. Okay, so a while ago the demonstration is just a proof of concept. Okay, of course the network is rather simple, but you can also go to the actual IFN transport where you can actually get the actual network, and then you can also run it there. Okay, so as discussion, the existing of IFN actually simplify the model greatly because we now can deal it functionally. Okay, and the IFN actually bring a fresh new perspective and simplification that we can find the relationship between the network structure, which you can get it from Google Map or OpenStreetMap, and network utilization. Okay. Can we do this using the traditional traffic assignment? The answer is yes. Yeah. So this above concept is not unique only to IFN, but the framework and the concept above, okay, will not be discovered if we did not do this simplification based on IFN. Okay. So in the summary, okay, we have developed a very simple generic framework, these 5 steps to identify the elementary policy, do some validity test and valid policy combination, okay, and then do feasibility test and search the optimum policy, okay. That can be applied in many other fields, okay, not just urban planning and city planning. Okay. And for this demonstration, we have applied this framework for generating optimal alternative solution, yeah, for traffic congestion. Thank you very much for this talk. Yeah. I would be happy to listen to your question or comment from the critics.
Thank you very much, Prof. Teknomu, for the talk on the systematic approach to generate optimal alternatives for traffic congestion solution. It was truly interesting to know more about ideal flow network. I myself have just learned this today, and using the combinatorial optimization on traffic, there are sure many probabilities on traffic solutions, and with the technologies we have now on our hand, it should become easier to find out the best policies on all the traffic problems. I suppose it is now time for the question and answer sessions. If you have questions for Dr. Teknomu, please just open your mic and ask the question, or you may type it on the comment section.
Thank you, Ms. Ruth. Thank you, Prof. Kardi. It's very interesting topic and clearly explained. We only need to adjust our mind that ideal flow network is different from neural network. However, ideal flow network also have a training phase, which in neural network involve learning to adjust the weight. Does this phase also need to adjust the weight? Because we need to consider that total inflow should same as the total outflow. Okay. Thank you.
So, yeah, thank you. The weight adjustment is done based on the formula. Okay, let me share screen a while ago. We go back to this. Here. Okay, so basically what you have is what is called capacity matrix. Okay. Capacity matrix is simple weighted adjacency matrix. Okay, so as long as your data can be put into capacity matrix, which is simple weighted adjacency matrix, okay, then you can form this into what we call stochastic matrix. So the computation is simple. Okay, so you have the capacity. Okay, without this, so capacity divided by the sum of the capacity. So say for example here, we have 5, 1, 1, 2. The total is 9, isn't it? Okay, so then this is basically 5/9, 1/9, 1/9, 2/9. Okay, so here we have 2 and 2, right? So we're supposed to get 1/2 and 1/2. Okay, so I'm get another one. Say, for example, here 3, 3, 4, right? So then the total, the stochastic matrix is just 3 plus 3 plus 4, which is 10. So 3/10, 3/10, 2/5. So stochastic matrix is just the capacity matrix divided by the sum in each row. Okay. Next, once you have this capacity matrix, we can from the stochastic matrix, we can calculate the ideal flow matrix. Yeah. So this is the formula. Yeah, which is based on Moll-Penrose inverse. Okay, so now suppose this is your stochastic matrix, then you can get the ideal flow matrix here directly. Okay, so this ideal flow matrix depends on the stochastic matrix. Yeah? Stochastic matrix depends on capacity matrix. So the real input is actually the capacity matrix. So the adjustment of the weight here, okay, you will see here the pattern. Yeah, the total, yeah, the sum of row is automatically the same as the sum of column. You see, this is 18.89. Here is also 18.96. The same. Here is 31.03. This one is also 31.03. So the pre-magic mean the sum of row is exactly the same as the sum of column. Yeah. So when you use this formula, you will automatically get that weight adjustment. So I hope this answer your question.
Yeah. So we can also use AFN to solve the traveling salesman problem.
I haven't tried that yet, so probably that's interesting topic we can explore together if you want.
Yeah. Okay. Thank you, Prof. Kati.
Yes.
Thank you so much, Dr. Erna. Do we have any more questions, or would you like to give comments on the talk of Professor Cardy? You may actually type on the chat box.
Yes.
Okay, I guess all is clear, Professor Cardy. So thank you so much for sharing your knowledge, most especially in demonstrating those different solutions and simulations. Now, moving on is the awarding of the Certificate of Appreciation to our plenary speaker. So may I request to flash the certificate?
Okay. Thank you very much.
Yes. Let me just read the citation. Certificate of Appreciation is given to Professor Cardi Tecnomo in appreciation of his invaluable contribution as a plenary speaker during the 3rd International Conference on Data Science, Artificial Intelligence, and Business Analytics held virtually on November 8 and 9, 2023. Given this 9th day of November 2023 at Medan, Indonesia and La Union, Philippines. Signed by our conference co-chair, the conference general chair, and the conference secretary. Thank you so much, and let's give our speaker a virtual applause.
Thank you.
Okay, so I guess everyone is now ready for
Sir
our
Christian,
parallel session. Yes, sir.
can we request for a photo ops with our plenary speaker and
Sure.
everyone?
All right, so inviting everyone to kindly open your cameras so that we can have a photo opportunity together with our plenary speaker.
Thank you very much, Dr. Cardi.
Thank you.
I saw you in Ateneo way back 2014
Okay.
with the Sir John Fernandez.
Yes.
Okay, so at the count of 3, I want you to give your best smile for the picture taking. All right.
Right.
So count of 1, 2, 3, smile. One more. 1, 2, 3, smile. Okay, once again, thank you so much
Thank you
for
very much.
joining with us, Professor Cardi Tecnomo. So I am encouraging everyone to